19,600 for blood pressure squared. The model becomes what we have here on the bottom. You do all the going to equal minus 4.58 plus 1.49 times whether he or she has cancer or not. This is what the model becomes for that type of person. It has this constellation of risk factors. Well, looking at that model, it says we can look at two people. And what does that model say about the effect of cancer? If you have cancer, your value for cancer is 1. Your value for your log odds of dying in the hospital is minus 4.58 plus 1.49 times a 1 is your value for cancer. So you get an additional 1.49 points to give you your log odds of disease. If you didn't have cancer, the model says your log odds of disease is equal to minus 4.58 plus 1.49 times 0, because you don't have cancer. Your value is 0. Or remember, any number times 1 is equal to itself. Any number times 0 is equal to 0. So we have two equations, two statements, what the model implies about a cancer patient's log odds of dying and a non-cancer patient's log odds of dying. I put a little 1 or a 0 under the p's to mean piece of 1 is the risk of the cancer patient, piece of 0 is the risk of a non-cancer patient. But I have two equations here implied by this model. If I subtract the bottom equation from the top, I'll get another equation. So first I'll subtract the bottom right-hand side from the top right-hand side. The minus 4.58 will cancel out. All I'm going to be left with is a 1.49. That's the difference of the two right-hand sides. The difference on the left-hand side is going to be log odds of dying if you have cancer, minus the log odds of dying if you didn't have cancer. But way back in junior high school, probably, you learned about logarithms. You learned about the law of logarithms. And one of the laws says if you take the log of one number, subtract from it the log of another number, that's the same thing as first dividing the first number by the second, calculate the quotient, and then taking the log of that quotient. So if you take the odds of dying for a cancer patient and divide it by the odds of dying for a non-cancer patient, that's what the odds ratio is, a ratio of two odds. So this 1.49 is nothing more than our log odds ratio. If you want, you can get rid of the log by taking the exponential function of that. So your odds ratio would be e to that number of 4.43. So what this means is that controlling for all those other factors in the model, odds of dying if you have cancer are 4.4 times that if you don't have cancer. So 4.4 reflects the unconfounded, adjusted effect of cancer on your outcome, controlling for everything that's in the model. And that is the main reason epidemiologists build models, to get adjusted or unconfounded odds ratios in this case. We'll be talking about this much more next week. But that's the main reason I think we build models. But there's a second reason we epidemiologists build models, and I think this was the real reason that this model was built in this example. That's for predicting outcomes. Because what I can do is go back to that same model, and I can, here I'm again using a regression model and expressing the outcome as a function of all these predictors. And now what it's going to give me is an estimated risk of developing the outcome, the risk of dying, based on all your risk factors. So confounding is not the reason we're doing this. We're trying to come up with valid estimates of each person's risks of dying. They have to be valid because that's how those numbers are going to be used by doctors, and it really doesn't reflect your severity. In other words, it's a wrong estimate, an invalid estimate. That means the care you're going to receive is not appropriate for what you should be receiving. So it's important you can convince people that the numbers you assign to people when you predict outcomes validly reflect their true risks, actual risks of developing the outcome. But if they do, that means we can go back to that model. And I know I'm not going to focus anymore on the coefficient of cancer or the coefficient of CP or the coefficient of age. I'm going to look at all the coefficients, because I want to know how all those coefficients influence P, the risk of a person dying in my hospital. The way I'm going to do that is I'm going to take a person and figure out what his value is for consciousness, type, cancer, CPR, infection, age, blood pressure, and the severity of blood pressure, and plug his values into the right-hand side of this equation, do the mathematics, and I'll get a number. And that number will be an estimate of that person's log odds of dying in my hospital. I can turn that log odds into an odds by taking the exponential function of that number. Now I'll have the odds of him dying in the hospital, and I can turn that odds into a risk. So for example, if I have a patient, again, who is conscious, who is non-emergent admission, who didn't have prior CPR, didn't have infection, let's suppose that person does have cancer, let's suppose that person is 50 years old with a blood pressure of 140, means a stored blood pressure of 19,600. I can plug in all person's log odds of disease as estimated by this model is minus 2.99. I can turn that into an odds of disease by taking e to that number. So that person's odds of dying in my hospital is 0.05. That's e to the minus 2.99. And finally, I can turn that odds into a risk by dividing the odds by 1 plus the odds. I'll say that person's risk of dying in my hospital is 4%, almost 5%, which might be much lower than other people. So maybe this is not a severely ill person. He doesn't require as much closely monitoring care as people whose risks were 40% or 50% or 80%. So typically, epidemiologists, I should say atypically, but commonly, epidemiologists do build regression models for the purpose of predicting outcomes, but more commonly, it's being used for controlling confounding. I hope to talk about both implications as we go through examples later today, but more importantly in the future weeks. So let's go and say some general statements, some general principles about regression models. And the way I'd like to do this is to link them to what we talked about last week. So first, a couple of general statements. This is the general form of all the regression models we'll be looking at. Today, next week, 2 weeks from now, 3 weeks from now. We're going to be talking about different types of models. And I'll talk about a few different types in a second, but they all have the same general expression. Their right-hand side looks the same. It's a summation of risk factors. That's what the X's are. X1 in the previous example was whether the person was conscious or not. X2 was whether the person was there for emergency admission or not. X7 was the age or the blood pressure of that person. So the X's are the risk factors that we have in the model, the predictors if we're building a prediction model, the exposure and the confounders if we're trying to measure the effect of the confounder. The coefficients, the B's, are what's estimated by the data set. And we'll be talking a little bit next week of where the numbers come from. Why the coefficient of cancer in the previous exercise was 1.49 or 1.47. Where did that number come from? We'll be talking about that in the coming weeks. But what determines the different types of regression models is what's on the left-hand side, the outcome you're trying to predict. Your outcome might be binary, as in the previous example, we're trying to predict whether a person dies or not in our hospital. Or it might be ordinal, we're trying to predict the stage of a cancer. Or it might be continuous if we're trying to predict the length of stay, the average length of stay of people. Different types of outcomes have different types of regression models. And so what's on the left-hand side is some function, that's what F means, of the outcome. It might be the risk of developing the main outcome category of interest if you have a binary outcome. It might be the average if you have a continuous outcome. But what determines the different types of outcomes, what's on the left-hand side, the type of outcome you're measuring. That also determines how the model is fit to the data set, what type of fitting algorithm you use, how the model determines what the values are for these coefficients, B0, B1. They come from some fitting algorithm. We'll talk a little bit about that. So, for example, we talked about in the very first class different types of outcomes. Now we're going to talk about different types of models. Remember the first thing I said, we have 3 general types of outcomes. We have categorical outcomes. Binary variables is an example of a categorical outcome. A nominal categorical outcome is an outcome with more than 2 categories. Binary is a special case of nominal, where the categories have no order. Ordinal means you have categories which have an order to them, say stage of disease. Continuous outcomes, there are different types. You might have a count, the number of times you were admitted to the hospital, the number of times you do a certain procedure on a patient. Or there might be a continuous outcome like length of stay or blood pressure or cholesterol level. Or another type of continuous outcome we see a lot is how long it takes for a person to develop an outcome, how long it takes a person, say, to die, time to death, time to hospitalization, time to remission, and things like that. Now, each of these different types of outcomes have different types of regression models. If you have a binary outcome, by far, the most commonly used regression model is something called logistic regression. If you have a continuous outcome, the most common method by far is a linear regression model. If you have a time to death censoring, the usual type of outcome is a Cox regression analysis. We'll talk about all